Hello everyone, today I will show the solutions to problems 5 and 6 of round 163 of the Prairie Math League. So we'll start with problem number 5. We have 3 pairs of twins who are arranged in 2 rows for a photo. However, there can be no adjacent pair of twins. This includes both sideways and in front of each other. And now we wish to find how many different photo lineups are possible. So now let's label the 3 types as A, B, C. So we can have, for instance, something like A, C, B, B, A, C. This is one possible way we can label the twins. Keep in mind that we're at this moment we're keeping twins, like pairs of twins, indistinguishable. So we don't, like, swapping these would result in our same arrangement for our purposes. We're going to change this like by the end of the problem, but we're just going to stick with this for now to make the problem simpler. So first we wish to find the number of ways to arrange the A's, B's, and C's such that we actually get a configuration that works. So for instance, something like AA would not work. Something like BB would also not work if they're like sideways or in front of each other. So now there are 2 cases for the front row. Case 1, we have a pair of twins in the front row. So in other words, we have like we have like something like A, B, A in the first row. In other words, there are 2 twins that are together in the first row. Now, so notice that if we have the twins like on opposite sides and some other person in the middle, well, this other twin this cannot be a B, otherwise we would violate this rule. So say the B is somewhere like here. But now, since it's not a B, the C has to go here. And then this is also a C, and this doesn't work. Notice that we've specifically picked A, B, and A, but this works with a loss of generality. So this could also be C, A, or C, or something like that. And the argument would still hold. Similarly, we can't avert this by putting the twins next to each other because this already violates this rule. So this also doesn't work, and thus we get that case 1 is not possible. Now for case 2, we have no pair of twins in the front row. So in other words, you have something that works like ABC. Now ABC is only one possible way to arrange them, but we're just going to stick with ABC for now. Then now there are 2 ways. Now we get to label this cell in 2 ways. We can either label this as B, or we label this as C. And we now show that once we label this specific cell, we can like fill in the rest of them in only one single way. This is because in this case, since we have a B here in front of the the C can't be here. So the C must be here, and the A must be here. The remaining A, and in this case, the B cannot be here because that's right in front of this one, so it has to be here, and then the A has to be here. And in both cases, we get 2 different ways that work given a single arrangement of the types of twins in the front row. Now we can arrange these types of twins in 6 total ways: ABC, ACB, BAC, BCA, CAB, and CBA, in 6 ways. And each way has 2. And finally, notice that how at the beginning of the problem we kept this indistinguishable. Now we're almost done the problem, so we can get rid of the condition. And instead of having A, B, or C, we have A1, A2, B1, B2, C1, and C2, where these 2 are twins, these 2 are twins, and these 2 are twins. And this is actually kind of trivial because consider these 2. We can assign every single A in 2 ways, either doing 1 and 2 or doing 2 and 1. So for every single twin pair, we have 2 ways, and since there are 3 pairs of twins, we have 2 cubed, which is equal to 8 ways to fill in like every pair of twins. Therefore, our answer is 2 times 6 times 8, 2 from here, 6 from here, and 8 from here, which gets 12 times 8, which is equal to 96. And that is option choice E. Now we move on to problem number 6. In this problem, the numbers 1 through 9 are placed at random into 9 squares of a 3 by 3 grid, for instance this one here, where every number is used exactly once. what is the probability that the sum of the numbers in each row and column is odd? Now, we're gonna repeatedly reduce the problem so that it becomes easier and easier and easier until we have something that is like much easier to work with. Now, consider every single row or column. Here we just have a row, but it doesn't matter. There's either three odds, 2 odds, 1 even, one odd, 2 evens, and 3 evens. And among them, this one is going to give us an even sum, so it doesn't work, and this one's also going to give us an even sum, which both violate this property. Therefore, we must either have 3 odds or 1 odd and 2 evens. Furthermore, among the numbers from 1 to 9, there are exactly 4 evens and 5 odds. So we know that an odd, like an even number, must appear at least once. So now we consider a very abstract form of our 3x3 grid where we just have an even, and we haven't drawn in. I haven't drawn in like the lines such, and like for instance here, because we don't really care about these lines, because we're just trying to abstract this. The point is, at some place there must exist an even. Now, these two, now consider this row and this column. Notice that this can't satisfy the 3 odds condition because we already have an even. Therefore, in each row and column, there must be another even. So for our row, let's pick the even here, and for our column, let's pick the even like here. Now, since we have those, we must also have some more rows and columns for which we require an even. Specifically, this row must contain another even, and this column must contain another even. But we already used up 3 of our 4 allocated evens, which means that we can only use 1 more even. And there's only one way this works, and it's to have this like right at the intersection of this column and this row. Now we've used all the evens, so now the rest of them are just odds. So whatever is not filled in is just filled in to be odd. Now notice that our evens kind of form a rectangle. And in general, this is true, like, it is true that for this condition to satisfy, the evens must form some sort of rectangle. For instance, this, or like this. But in both cases, they must form in any case, they must form a rectangle. And now we've basically reduced our problems to finding out the number of rectangles that exist within a 3x3 grid. So, if we look at this grid here, a rectangle that in this grid must have both a starting column and an ending column. So for instance, this could include something like this. It has a starting column for like the left bound of the rectangle and an ending column for like the right bound of a rectangle. So we just basically have 2 arrows pointing into the grid. Now, there are 3 columns in total, and we must choose 2 of them to be our bounds. Therefore, there are 3 choose 2 ways to choose the left and right bounds of the rectangle. And the rows have a very similar pattern. Out of the 3 rows, there must be 2 bounds for which they're like rectangles. So like, sorry, there must be like two bounds that are chosen in 3 choose 2 ways. So this gives us a total of 3 choose 2 equals 9 rectangles in total. So now this is out of a total of, well, we're trying to find the number of ways to put evens and odd in a grid. So for instance, we can have even, or something. But we're just counting the total right now. But there are 9 cells, and we're choosing any 4 of them to be even. So in our total count without this restriction, in our like overall count for the denominator, we have to have 9 choose 4 equals 126 ways. And now all we have to do is divide this and take the fraction to get option choice A, 1 over 14. Now you may be wondering why we get to like use E's and O's instead of like using the numbers themselves. Well, it's because like just like this last problem, exactly how we arrange like the twins, or in this case, the E's and O's, doesn't really matter at all. We can have, for instance, like E's appearing like 1, 2, 3, 4. But in the total count, it would basically correspond to the same thing. In other words, it's the exactly the exact positions in which we put our evens and odds does not is kind of independent from the way we position the evens and odds in the first place, which is why we don't need to consider the evens and odds. Like we don't need to assign every single number to an even to every single cell for this specific problem, and we can just say option choice A and we're done. Anyways, thanks for watching.